Pluto made them come up and down. Pluto's circle crosses that of each other planet. Pluto, the confounding little planet at the external extents of our nearby planet group, is working up further in the universe of space science. Continuous reports suggest a possible revelation with Neptune, raising concerns among specialists and space aficionados. Distinct figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the ramifications of this cosmic event. But how did Pluto end up on an intensive course with its bordering planet, and what could this great battle mean for life on Earth? Join us as we unravel how something important just collided with Neptune and how analysts were left befuddled by this huge inconsistency. Pluto, once hailed as an obvious planet, went through a change in its status, being renamed as a dwarf planet because of its exceptional orbit. Regardless of this downsize, Pluto still charms and interests the cosmic community. Later assumptions from regarded analysts like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's direction, potentially meeting with Neptune, indicating an impending series of accidents between the two eminent bodies, which could have critical repercussions for Earth. Pluto's journey across the Sun stands out in light of its exceptional properties. Inside our planetary association, its orbit is unusually elongated, crossing at a beautiful angle. Since its discovery in 1930, Pluto still can't seem to finish a full revolution around the Sun. Adding to its character is the especially extended condition of its orbit, a departure from the more round ways followed by the major planets. Aside from Pluto, its orbit drifts off by 17 degrees from the ecliptic plane, giving its path a more serious grade compared to other planets. The mix of Pluto's inclination and its bended orbit gives layers of intricacy to its orbital pattern. One critical angle is its incidental combination with Neptune's orbit for around 20 years during each cycle. Pluto ventures closer to the Sun than Neptune, contradicting assumptions based on their separate positions in the nearby planetary association. Plunging further into Pluto's orbit, taking note that it is not an ideal orbit, but rather an elongated oval, we find that this interesting orbit results in huge variations in Pluto's distance from the Sun during its journey. At its nearest approach, Pluto goes inside around 30 galactic units, AU, of the Sun, while at its farthest point, it reaches more than 49 Australian dollars away, twice the distance of Neptune from the Sun. Also, Pluto's orbit is tilted at a huge angle relative to the orbits of the major planets in our planetary group. This inclination not only adds to the intricacy of its orbit but also plays a huge role in its interactions with other celestial bodies, especially Neptune. When Pluto crosses Neptune's orbit, their gravitational fields impact each other, shifting their directions over time. The complicated dance among Pluto and Neptune highlights the unique nature of our nearby planetary association, where Pluto, once considered to be a singular stray in the outer reaches, now demonstrates its interconnectedness with Neptune. Each body applies gravitational forces that shape the orbits of others. In later years, upgrades in observational technology have allowed space experts to track Pluto's movements with great precision. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer planetary system. However, the chance of an immediate crash between Pluto and Neptune remains low, though it cannot be entirely ruled out, prompting scrutiny from the scientific community. Despite its humble size and remote location, Pluto continues to draw attention and interest from researchers and enthusiasts alike. The question arises, why hasn't there been a crash between Pluto and Neptune? The answer lies in the gravitational pull of other planets. Astronomers began studying Pluto's orbit shortly after its discovery, and its path baffled them. Unlike most planets, which follow nearly the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery grew when they realized Pluto's path crosses Neptune's. Despite these complexities, Pluto's orbit remains stable, illustrating the intricate mechanics of space. Figuring out how three celestial bodies, Pluto, Neptune, and the Sun, move and interact gravitationally is a huge challenge. It's like trying to predict where they will go based on where they start and how they pull on one another. For Pluto, this challenge shows how its orbit, Neptune's orbit, and the Sun's coordinates all work together, like a simulation. Terms like precession, libration, and VSOP help researchers in solving this cosmic riddle. A simulation is crucial for keeping planets in their orbits. When Pluto crosses Neptune's path, it's at least 90 degrees away, keeping them from crashing. Libration ensures that when Pluto approaches Neptune or other large planets, it's well over their path, reducing the risk of an impact. The VSOP model, named after researchers von Zeipel, Stevens, and Opik, explains why Pluto's orbit seems unusual but remains stable over time. Despite the turmoil in space, certain patterns and rules keep things together. These rules prevent Pluto's orbit from being unstable and prevent crashes with Neptune or shifts in its direction. The chance of orbital chaos shows how a celestial body's path is extremely sensitive to where it starts. This is well demonstrated by Pluto. Even small changes in its position or speed can disrupt its orbit over time. Researchers use virtual simulations to figure out how Pluto moves in space. These simulations use complicated math to recreate how Pluto interacts with other space objects like Neptune. By tweaking these simulations slightly, astronomers can see how small changes can modify Pluto's orbit. In the late 1900s, these simulations revealed something intriguing about Pluto's orbit. Despite factors that should make it stable, Pluto's orbit can still be erratic. Just a small difference in where Pluto starts or how fast it's moving could make huge changes over many years. Anyway, even with this unpredictability, Pluto's orbit remains stable for a long time, like billions of years. This shows that even though Pluto seems tumultuous, its journey across the Sun follows a kind of pattern. Predicting what will happen with planets like Pluto, which have unusual orbits, is difficult. These systems are so erratic that it's challenging to understand what will happen in the long term. Simulations help us learn about potential outcomes, but they also show us that we can't predict everything with certainty. Understanding Pluto's orbit is important, especially when we consider if it could crash into Neptune in the future. This knowledge helps us understand our solar system better. Pluto's orbit teaches us that even orbits that appear unstable can remain stable due to gravity and how things move in space. Continuing to study and analyze these issues is essential for expanding our knowledge of the universe and our place within it. When we explore space, we realize that things can be strange, and Pluto's orbit is a great example of that strangeness. Pluto's orbit isn't like those of other planets. It's more oval-shaped, meaning it's not a perfect circle. Sometimes it even draws closer to the Sun than Neptune does. This could make things interesting since Neptune is also moving along its path. There's a small chance that Pluto and Neptune could collide, but even with its unusual orbit, such a collision is unlikely. Mercury, and this has starting questions like, consider the possibility that Mercury is really inhabitable, and on the off chance that it is, what feasible ways of life structures should exist on the planet? Up until this point, the floor of present-day Mercury has been very interesting, similar to our Moon. The planet appears to have several impact craters, much like the Moon, which has long been filled with contentions and paranoid notions about extraterrestrial beings. Many argue about the possibility of extraterrestrial moon bases due to its surprisingly large number of craters. Some of these craters take puzzling shapes, like arches. Despite the lack of evidence, many have speculated about the presence of ultramodern species on Mercury, suggesting that some craters may have been caused by shuttles, such as NASA's Messenger spacecraft, which created a huge crater when it collided with Mercury's surface on April 30, 2015. Today, there are countless craters, cracks, edges, and even lava eruptions. So, consider the possibility that these various craters were caused by similar extraterrestrial shuttles or alien activity. There are other astounding facts about Mercury that have fueled conspiracy theories. For instance, the ice water stores located inside the craters at the planet's north and south poles. Recent studies by the Planetary Exploration Institute suggest that the planet's north pole could have the right conditions for extreme storms, which function similarly to those on Earth, only they are hidden beneath the planet's surface. This conclusion was drawn from photos taken by NASA's Messenger spacecraft, which were turned into a map using this data. Researchers noticed that there are certain salt ice sheets on the planet that are filled with unstable mixtures that could potentially support life. Thus, even within the deadly proximity to the Sun, scientists agree that there is a possibility of extraterrestrial creatures or ultramodern biolife existing on Mercury if we dig deep enough. One of the greatest achievements of NASA's Messenger spacecraft was creating a map of Mercury, capturing all the craters and bowls on the planet's surface. This gave NASA researchers the opportunity to study the planet's geography in depth. But even more importantly, the spacecraft also revealed that Mercury has a surface composition of 46% oxygen, 12% magnesium, 26% silicon, 7% aluminum, and 4% calcium. Researchers also found that the planet has an unusually high presence of sulfur but low levels of iron. This discovery sparked debates within the scientific community, as it sets Mercury apart from the other planets in our solar system. Planets in the solar system are generally recognized to have more iron than sulfur, especially in their cores. Seeing a planet that does not follow this standard intrigued scientists and sparked increased interest in Mercury. Recently, researchers also noted something surprising about the planet: it has a distinct dusty ring around it. This sparked further debates, as many scientists believe Mercury is too small to have a planetary ring. In our entire solar system, only Jupiter and Saturn are known for their rings. Saturn's rings are massive and easily visible from Earth, consisting of billions of pieces of debris, ranging from small to enormous. The substances that make up Saturn's rings include water ice and rocky material. Researchers believe these rings formed during the early days of our solar system, and the massive size of Saturn and Jupiter allowed them to pull in the material needed to form such rings. Saturn is about 10 times the diameter of Earth, and Jupiter, nearly 12 times the diameter of Earth, has attracted around 95 moons, forming its own miniature ring system. Given the immense size of Saturn and Jupiter, it is understandable how these planets were able to attract vast amounts of cosmic material to form their rings. However, this raises the question: how does Mercury, the smallest planet in our solar system, form its own rings? For reference, Mercury's dust ring is about 9 million miles wide. Researchers are still uncertain about how these rings were formed, but many speculate that they may come from asteroids, which could have impacted the planet at some point in the past. A group of researchers led by Dr. Peter P., an associate at NASA, suggested that this theory could be correct. According to him, it is not uncommon for objects to continually collide with planets like Mercury, which lacks a significant atmosphere. It is plausible that these collisions could have launched debris that eventually formed the visible dust ring we see today. Other scientists in the academic community seem to agree, suggesting that the constant bombardment of Mercury's surface by meteorites and other disasters may have contributed to its small size and thin mantle. Mercury's outer shell, also called the crust and mantle, is much thinner compared to Earth. It is only about 250 miles thick, whereas its core makes up around 85% of the planet's volume. Many leading minds speculate that Mercury must have experienced catastrophic events that stripped it of its outer layers, leaving it in the state we see today. Despite all these theories and speculations, there is still a need for NASA and other research organizations to dig deeper into the mysteries of Mercury to answer all of its current-day questions.